In this lecture, let us talk about discrete time systems. Okay, so far we talked about signals and how the signals will interact with systems, right? So that is, we take discrete time systems, and the input is, let's say, x of n, and we would like to see what is the output y of n, okay, and see how it can be characterized in the transform domain, in the frequency domain, how your output looks like. So we have learnt about discrete time Fourier transform, then discrete Fourier transform, and Z transform till now. Okay, so discrete time Fourier transform, discrete Fourier transform, and Z transform of signals. Now the next question is, how do they help in characterizing discrete time systems? Well, one of the things that you should appreciate is that any signal, be it analog or discrete time, any signal can be decomposed into sinusoids, right? That's what we understood from our DFT, DTFT and Z transform. Okay, so decompose into sinusoids when you take Fourier transform, and when you take a periodic signal in the continuous time domain, we take Fourier series. Periodic signal, we take Fourier series, and we know that the Fourier series is summation of sinusoids, an cos n omega t plus bn sin n omega t, like that. Okay, so we have summation of many sinusoids of frequencies which are harmonically related. See, omega naught, these are omega naught, and you have 2 omega naught, 3 omega naught, and so on and so forth. That is, there is a fundamental frequency. There is a fundamental frequency, and this fundamental frequency f naught is given by 1 by 1 divided by the period. Then you have the second harmonic, and you have the third harmonic, and so on and so forth. When the signal is not periodic, then we take Fourier transform. Okay, so when the signal is not periodic, then what do? We took Fourier transform, continuous time Fourier transform, CTFT, which means that the spectrum consists of all frequencies. Here the frequencies are harmonically related, fundamental frequency, second harmonic, third harmonic, but in the signal is not periodic, then we took CTFT, and output of the CTFT contains all frequencies. Okay, that is a continuum of frequencies. Okay, not just fundamental frequency components. Okay, not just fundamental and its harmonic, and in this case, no harmonics. No harmonics. For a non-periodic signal, that is the signal which exists only from, let's say from like this, minus t to plus t. What is the fundamental period? Fundamental period is 0, right? Therefore, what is the fundamental frequency? It is 1 by 0, which is infinity. Therefore, starting from 0 hertz, right, this is infinity hertz. Therefore, starting from 0 hertz, we grow up to infinity hertz. All frequencies exist. All frequencies exist for a periodic signal. but it can also be looked upon as a continuum of sinusoids, right, because the sinusoids exist from 0 Hertz up to all the way infinity Hertz. And therefore, any signal, be it continuous time or discrete time, can be thought of a superposition of sinusoids. Okay. So, any discrete time signal can be thought of as a superposition of sinusoids. Okay. So, therefore, discrete time signal is equal to summation of sinusoids. Therefore, the spectrum between two adjacent sinusoids may be infinitesimally small. Infinitesimally small. That is, we denote by d omega. That is why we use integral, right, x of t multiplied by e to the minus j omega t and dt for Fourier transform, and inverse Fourier transform we wrote x of j omega times e to the plus j omega t times d omega. So, we put the integration and from minus infinity to plus infinity. And we also know that any sinusoids can be, let us say, sin omega t can be written as a sum of two exponentials. One is e to the j omega naught t and the minus of e to the minus j omega t divided by 2j. So, if you take sin omega t or cos omega t, does not matter, this sinusoidal components can be written in terms of two exponentials, and therefore, an exponential signal is the most elementary signal as far as characterization of a system is concerned. Okay. So, if we know the response to a sinusoid or an exponential signal, then you know the response to all other signals, because any signals can be decomposed into sinusoidal signals, and the sinusoidal signals can be written in terms of exponentials. Therefore, the moment we know the response of a sinusoidal signal or an exponential signal, then we will be able to know the response of any arbitrary signal. So, that is what we are trying to say here. So, we try to find out the response to an exponential signal, and for that we specialize our system to Lti systems. Right. So, Lti means linear time invariant systems. For linear time invariant systems, we know that the output is given by the convolution of the input and the impulse response h of n. So, the impulse response of the system is h of n and the input is x of n. Therefore, what is my y of n? If you write in terms of convolution sum formula, summation x of n minus k h of k, and k goes from minus infinity to plus infinity. I should have written the other way around, it does not matter. X of k h of n minus k, where k goes from minus infinity to plus infinity. And now, if this system we apply an input x of n, which is equal to e to the j omega n, then the corresponding output will be what? You substitute here, summation of e to the, I am taking this equation, e to the j omega times n minus k times h of k. Now, rearrange the summation. This is e to the j omega n, e to the minus j omega k and h of k. and now this e to the j omega n is independent of the summation. Therefore, you can pull out of the summation e to the j omega n summation and e to the minus j omega k times, let me write h of k here, e to the j omega n. And you notice that since this term is independent of what? Independent of n. The left hand side you have y of n, here there is a time parameter n, and here also the time parameter n. But if you look at this guy, then this is independent of n. So it can be simply replaced by a constant. Let me call that constant as capital H of e to the power j omega, and this one is e to the j omega n. So my y of n is e to the j omega n multiplied by capital H of e to the j omega. Okay, and this one is constant. This one is a constant. That is, when I say constant, what does it mean? It is independent of n. Therefore, y of n is a constant, that is capital H of e to the power j omega multiplied by e to the j omega n. Okay. Now, such functions which when supplied as an input to the system produces an output which is a constant multiplied by the same function called Eigen Functions. See, I have the discrete time system and the input is e to the j omega n, x of n I am going to assume e to the j omega n, and what is output? Output is a constant time capital H of e to the power j omega times the same function which you applied in the input. Both are same function. So whenever you have this type of situation, then you call this e to the j omega n Eigen function. It is called a Eigen function, EIGEN, Eigen function, e to the j omega n. So e to the j omega n is an Eigen function of linear time invariant discrete time system. Okay, and you notice that what is h of e to the j omega? This constant, right? This we called h of e to the j omega, capital H of e to the j omega. What is this? What do you think this is going to be? H of capital H of e to the power j omega is summation h of k e to the minus j omega k. Now, don't you see, this is precisely the definition of what? DTFT, discrete time Fourier transform. Therefore, capital H of e to the power j omega is equal to discrete time Fourier transform of the impulse response h of n. Okay. Therefore, this capital H of e to the j omega is known as the frequency response. Frequency response of the system. Okay. Therefore, this h of e to the j omega is the quantity which is a characteristic of the system. By using this e to the j omega, capital H of e to the power j omega, we will come to know the behavior or the character of the system. Okay, just as h of n is the characteristic of the system in the time domain. Similarly, h of e to the j omega is the same characterization as h of n, but transformed to the frequency domain. Okay, so therefore, capital H of e to the power j omega is called frequency response because it involves what? Why is it called frequency response? Because it involves omega. Okay. Therefore, it shows the complete frequency behavior of the system, and in general h of e to the j omega will be the complex frequency. Capital H of e to the power j omega will be a complex quantity. In general, need not be complex, sometimes it may be real and sometimes it may be complex. So, in general it is a complex quantity. So, whenever you deal with a complex quantity, then that complex quantity can be written in terms of magnitude and phase function. So, capital H of e to the power j omega can be written as magnitude and its angle, phase angle. So, how do you denote this phase angle? E to the j times angle of h of capital H of e to the power j omega. That is it. Okay. Now, we know this is magnitude and this is phase, right, and we know this magnitude is what? It is real and it is even function. And what about phase? Phase is odd function. And is phase real? Phase must also be real quantity, but it is odd function. Okay. And angle and phase are equivalent terms. Now, it is interesting to see that this e to the j n omega leads to discrete time systems, leads to h of e to the j omega times e to the j omega n, isn't it? Now, because the system is linear, if you take the real parts of this, because the system is a linear system, right? If it is linear, then you can take real part in the input side as well as you can take the real part in the output, both should be equal. Okay. So, if you take the real parts of both sides, they should be correspond to each other. E to the j n omega gives rise to h of e to the j omega e to the j omega n. Then if you take the real parts of e to the real part of e to the j omega n, then this gives rise to real part of h of e to the j omega n times e to the j omega e to the j omega. That is it. In other words, if we know the response to the e to the j omega n, then you know the response to cos n omega and sin n omega also. Why? Because real of e to the j theta is equal to what? Cos theta. Imaginary part of e to the j theta is what? Sin theta, right? Therefore, once we know the response to e to the j n omega, then we will be able to easily find out the response of cos n omega and sin n omega. So, how do you do that? E to the j n omega gives rise to capital H of e to the power j omega times e to the j omega n. As I said, this is a complex quantity and the complex quantity can be written as modulus of capital H of e to the power j omega and e to the j times angle of h of times e to the j omega n, this one. Now, these two are phase terms, combine those two guys, magnitude of capital H of e to the power j omega times e to the j times omega n plus angle of h capital H of e to the power j omega. So, this is my input and this is my output of the discrete time linear time invariant system. Linear time invariant system. Okay. So, we know that what is cos n omega? Cos n omega is real part of e to the j n omega. Okay. Take the real part on both sides of this equation. So, real part of e to the j n omega is equal to real part of h of e to the j omega, take modulus, and then e to the j omega n plus angle of h of e to the j omega. Now what is the left hand side? It is cos, I am sorry, this is not equal, this is gives rise to, and this also gives rise to. Therefore cos n omega becomes, anyway this is a constant term, you can pull out of from the real, I mean it's a even term and a real term. So you take h of e to the j omega magnitude, and this you take the real part. What is the real part of that? Cos of that phase angle omega n plus angle of h of capital H of e to the power j omega. That's it. And in a similar manner, I have an input sin n omega. Okay, then all that differs is, instead of cosine, I have sine of omega n plus angle of h of e to the j omega. That's it. Okay, and this gives this expression, and this expression gives the steady state response of the system. You might have studied this in your other course like control systems. Steady state response of the system. Okay, so steady state response of the system to either an exponential signal or a cosine signal or a sine signal. So this value e to the j n omega is the most important signal. Once we know the output of a system for this guy, then we will be able to find out the output for any other signal. Doesn't matter, no matter what signal you have, you can find out. Therefore this is the most important signal in practice. Okay, it is in the frequency domain, right? In the time domain, what is the most important signal? Del of n. This is del of n is the most important signal in the time domain. Why is it most important signal in the time domain? Because if you know h of n, then you know the total characteristics of the system, right? So through this del of n, we will be able to find out h of n, right? So correspondingly in the frequency domain, it is e to the j n omega. So if you know the response to e to the j n omega, or e to the, that is, you know h of e to the j omega, or if you know the response to the del of n, which is h of n, if you know this, then we will be able to find out the response of the system very easily for any type of signal. So these four are important thing: del of n, h of n corresponding to in the h of e to the j omega, del of n, e to the j n omega. Very, very important signal in the signal processing. Okay, so let me stop here. In the next example, we will consider an example, and then we will try to find out its response, okay, in terms of magnitude and phase. Thank you very much.